My topic is mass oscillating on a pendulum. The first thing we'll begin with is the pendulum's potential energy. The equation for potential energy is EP of the pendulum is equal to mass times gravity times height. Gravity is a given at 9.81 meters per second squared, and the mass can be identified on the load of the pendulum. In this case, it's 40 grams. But what about height? There's a concept that must be taken into account before determining how to use height, and it has to do with the pendulum's equilibrium. If the pendulum is not in motion, that means the height value is 0, because it is at its lowest point. If the pendulum is in motion, then height is not determined based on how high the pendulum is off the ground, but it's determined based on the difference in height between the pendulum in motion and its equilibrium, also known as 0. To find the distance between 0 and the pendulum, subtract your length from cos theta. Or for short, you can do L bracket 1 minus cos theta. Using our information, we have the length, which is 20 centimeters, bracket 1 minus cos 45, which is our degree up in the top. And that's going to come out to 5.85 centimeters. Now that we have our height, we can move over to the potential energy equation. EP of the pendulum is equal to mgh. Mass is 40 times 9.81 times 5.85. That's going to come out to 2,295 joules. Alright, now we're going to look at restoring force. Restoring force is the energy exerted to direct the pendulum back to its equilibrium. Restoring force is equal to mass times gravity to sine theta. Here I've drawn two triangles. Triangle 1 models the pendulum using the distance equation to determine how far apart the pendulum and the equilibrium are in centimeters. And triangle 2 isn't representing the distance, but it's showing the amount of restoring force being exerted. Going back to triangle 1, we need to solve for theta by rearranging the d equation to become theta equals d over length, distance over length. When angles are small, like in pendulums, we can assume that the theta value is almost equivalent to sine theta. Now we can say sine theta is equal to distance over length. Sub that into the equation and you are left with mass times gravity divided by length times distance. Will give you your restoring force. In this case, 60 is our mass, 9.8 is gravity, divided by 20, which is our length, times 11.47, which is our distance. And that's going to give you 337.5 kg meters per second square. Finally, we're going to take a look at the period of a pendulum. The period of the pendulum measures the amount of time it takes for it to complete one full cycle back and forth. Base equation for period is 2 pi square root ml over mg. Cancel out the m's and you're left with 2 pi square root L over G. Simply in our case, we can go 2 pi square root, our length is 20, our gravity is 9.8 as always, comes out to be 0.70 seconds. Therefore it takes 0.70 seconds to make one full cycle around.